carboxylic acid derivatives. And so what we have left is our amides and our nitriles. In the preparation of amides, turns out these were all carboxylic acid derivatives before. We start with our acid chloride. We can react that with 2 equivalents of our amine. Don't know why I drew it that way, but anyway. And we've looked at this one before in the reactions of chlorides. We can do the same thing with an anhydride. And I'm just showing the amine here, but again, it could be the primary, the ammonia, but I could have a primary, a secondary. And I can also do this with esters. Esters are a little less reactive, but the same process occurs. Sometimes you'll see esters with heat, but heat here is just necessary to make it go relatively quickly. It's not necessary for the reaction to actually get over the energy of activation. It's just going to react slower. And of course, we saw these as reactions of acid chlorides, anhydrides, and esters. The hydrolysis of amides, like with the other ones, right, or at least with esters, we have both the acid catalyzed and the base promoted. With the acid catalyzed, we have the amine, or the amide, sorry, the amide, and now we're going to add heat to this. So as we go to less reactive carboxylic acid derivatives, our reagents have to increase in their energy. And so we go from water with chlorides to water and acid to water, acid, and heat. Right, and that can give us a carboxylic acid. So if we look at the mechanism on this one, first thing we're going to do is a proton transfer. And then once we've activated that, we can get a nucleophilic attack, right? So we've activated our carbonyl. We get nucleophilic attack at the electrophilic carbon of the carbonyl. Okay. Then we're going to get a proton transfer. Here I'm going to use a generic base, but most likely in these conditions, it's going to be water. Let's put it on the other side so you don't get confused. Now we're going to get another proton transfer. All right, so the lone pair is going to pick up that proton. Oops, arrow's going the wrong direction. Okay, and then here we have loss of a leaving group. So the electrons come down. All right, we can lose the amine, the ammonia. And then we get a proton transfer here to get us to our final product. And again, most of this is reversible. Except for that last step, right? Once that ammonia comes off, gets protonated, then the last step is not reversible. So this hydrolysis goes to completion. Because I'm in an acid conditions, the amine is a very good base. I'm going to protonate it. Once I protonate it, it's no longer nucleophilic. That last step can't be reversed. Okay. Okay, questions about acid catalyzed? Okay. This one, remember this one, foreshadowing the lecture here. Remember this one when we get to nitriles. The other thing we can do is base promoted. With the base promoted, we're just changing the conditions to a base. But we've got to do it in 2 steps. And notice here, it's not only sodium hydroxide, I'm going to be adding heat. Again, the amide needs a little bit more encouragement. In this case, the heat is essential to get over the energy of activation. But after both steps, I ended with the carboxylic acid. So in the base promoted, the first step is not proton transfer, it's nucleophilic attack. Then we can get loss of leaving group. Notice one of the reasons we've got to have heat here, right, is that we are losing the NH2 minus. So that's a very unstable. It's not as unstable as a carbon, right? But it's not in the same order as the OH minus. And then this will come back there. And that's the end of first step, right? So this was all, let's use a different color, right? This was all step 1. Then step 2. Then we protonate our acetate to get us to our final product. Okay, questions about base hydrolysis? Both of these work pretty well. There's a tendency to do the acid catalyzed because the energy is actually lower, but the base will work, right? So the base will work. So both esters and amides both have an acid and a base hydrolysis process. Remember, with chlorides and anhydrides, all we had to have was water. Okay, reduction of amides. In this take, we take an amide and we reduce it to the amine. reason we don't end up with the alcohol is because the alcohol is a better leaving group than the amide. So if we look at our process here, right, the hydride attacks the carbonyl. And then at this point, right, that's a poor leaving group, right? So we actually get a this reacting with the aluminum. And I'm gonna put an R3 there. And then this reacts with another hydride. And we get loss of the that ends up giving us this. And the just like with before with the aluminum, with the oxygen species, the nitrogen can also make a complex with the aluminum, and so that's why we need water in the last step to remove that. Okay, but at this point right here, right, the NH2 is not a great leaving group, so I don't have that coming down and kicking that off, right? Okay, so for nitriles, right, we already know how to make those. We can make those from our other acid derivatives. We can then turn the amide into a carboxylic acid with either acid or base, right? And then we can reduce amides down to the amine. If we think about nitriles, versus amides, right? If we think about these two, what's missing when we go from an amide to a nitrile? Well, looking at the nitrile, we have the R, right? The alkyl group. We have the carbon and we have a nitrogen. When we go to the amide, what do we have? We have the R, the carbon, oxygen, nitrogen, and 2 hydrogens. What's an oxygen and 2 hydrogens? All right, what's missing between those two is water. So one conceptual way to think about nitriles is they are dehydrated amide. So they have similar reactivities as amides, and we'll see that if we can add a reagent that can help dehydrate an amide, we can turn amides directly into nitriles, or at least primary amides. Okay, preparation. The first one goes back a ways, right? If we have a good SN2 style electrophile, and we add a sodium cyanide, right? We can get, so the reaction here, it goes all the way back to our first mechanisms, right? This is just an SN2. So one way to make nitriles is to react electrophilic carbons, electrophilic alkyl halides with just nitriles, potassium or sodium nitrile. We can also make nitriles from amides. Again, the difference here is loss of water. One thing that's very important is it has to be the primary. right? It has to have NH2. If it's not NH2, then this isn't going to work. So we need something that will help get rid of water. Turns out that our thionyl chloride friend, oh, wrong position, will help us get there. Let's look at the mechanism. Okay, we end up with the sulfur tetrahedral intermediate with the nitrogen positive. Then, like our other thionyl chloride reactions, this will come down, kick off the chlorine. Then if we use a generic base, it could be the chloride, but again, chlorides don't make great bases. We can pick up a proton. And again, promoted with a base. Then we get the cascade, right? Like we see with other thionyl chloride reactions. And we end up with a nitrile. Okay, questions about this one? Again, similar processes. So hydrolysis. You can do acid catalyzed. Okay, the nitrile, lone pair in the nitrile is going to be protonated. That's going to activate the nitrile to attack by a nucleophile. So this is going to come in and attack there. Then we're going to do a proton transfer. So water picks up an excess proton here. And then we're going to get another proton transfer, this time to the nitrogen. Then we have the protonated nitrogen. And then lone pair on the oxygen comes down to create the more stable species. And we get right there. And that's where it intersects with the amide hydrolysis. So in the process of hydrolyzing the nitrile, we end up with, notice this is the protonated amide. All right. So if we go back to that one, I'll give you some more time to copy it. But if we go back up here, right, the first step was to protonate the amide. And if you take this species and rotate it a little bit, you notice that that is the same as this. Okay. So we get protonation, nucleophilic attack, we get proton transfer, then we get loss of this pi bond, right? So we create the double bond, giving us this, which is the protonated amine, and then that will continue through the mechanism, right, to the acid. Okay, questions about this one? Like with the ester and the amide, the nitrile also has a hydraulic base promoted. Not seen as often, but it does work. And whenever I'm putting sodium hydroxide in here, consider this to be pretty strong sodium hydroxide. Here we'll need water, usually heat. And then of course, to get it back to the acid, we'll need the protonation. Mechanism is similar to that. After the first step, it mimics the amide. And of course, the hydrolysis of nitrile to get the carboxylic acid is one of the reasons that the nitriles are carboxylic acid derivatives, right? So they look a little different, but they're the derivatives. Okay, granular addition. What happens in this case and why we end up the ketone and not a nitrogen containing species is that the Grignard is going to attack the carbon, right? And you can think about it forming this complex to start with. But as soon as I put it in acid, that's going to get me to this. And what would I call this functional group? What's a carbon double bond nitrogen? Remember, this is an imine. And what happens if you put imines in acid and water? Well, in acid and water, they hydrolyze back to the ketone. Okay, so going back to reactions of aldehydes and ketones, we form an imine. So the attack of the grignard on a nitrile creates an imine, and then that imine hydrolyzes with acid and water to the ketone. So I only get one addition. So this is a substantial difference to the other carboxylic acid derivatives, right? If I had added the ester, I add the grignard twice, but with the nitrile, I only add the grignard once. And I could put excess on here. It's not necessary to put excess, you'd still get the same product. Reduction of nitriles is like the reduction of the amides. We end up with the amines. Similar process. Okay. So we finished up amides and nitriles. So let's look at a few. Try this. And we'll take a little time on these. They're multi-step synthesis. Remember, it's always good to draw out each step. Give you a little time to try these. Again, draw out each step. Okay, let's go ahead and take a look at the first one. The first thing that's going to happen is our nitrile is going to react in an SN2 fashion with our bromide. What's the thing you should notice about this reaction? Besides making it a nitrile, it also did what? I've changed my functional group, but I've also changed I've added one carbon, right? I've changed my carbon skeleton. So the nitrile addition to electrophilic carbons also changes your carbon skeleton, but it can only do one, right? And it turns out that adding one carbon is sometimes odd. So that was the reason for the Grignard with CO2 being such an important reaction, that adding one carbon can actually be tough. Okay, so we do this, and then the next step, we're doing the reduction. And the lithium aluminum hydride is always paired with the second step, which is water. So in this case, I don't need to show two more steps, can do it in one step. And this will get me to the reduction of the nitrile, right, to the amine. So this is my product. And again, always try and draw them out. It'll help you get them in the long run. The next one, again, this one is not a paired set, so therefore I want to draw it out. So let's give ourselves a little bit of room. After the first reaction, I'll form the amide, and then the amide with SOCl2, right? As long as that amide is a primary, will give me and sometimes it's good to go ahead and count. So here we had 1, 2, 3, 4. So here 1, 2, 3, 4. Questions about this one? And then the last one. This is a paired set. I need to think about what's attached to that Grignard. So it's 2 carbons. So if I look here, I had 1, 2, 3, 4. On this side, I had 1, or I could say 5, 6, right? So that when I get over here, here's 1, 2, 3, 4, and then it's 5 and 6. And again, the intermediate here is right, and then that gets hydrolyzed. Okay. Questions about either of these three? Pretty straightforward. The next chapter we're going into is alpha carbon chemistry. And we'll be in this chapter for a while. It's about as big as the carboxylic acid derivatives chapter. And in this chapter, we're going to be dealing with enols and enolates. So if we look at a carbonyl, one position away from that carbonyl is known as the alpha position. The second one is known as the beta. Then we get to the gamma, right, and the delta. And it turns out those positions are the ones that we're going to be focusing on. And one of the reasons that those two positions are important is that if we look at those positions, it's actually the acidity of these two protons. So in this structure, oh, added one too many. These protons are going to be acidic because if I used a base to abstract one of those, I could easily make this species here right? So it has resonance. So when we look at that pKa, if we look at that acidity, it's going to make those alpha hydrogens different than the betas. If I extract for the beta or the gamma, I wouldn't see the same thing. Okay. Yes, sir. Because of the resonance here, they have a higher acidity. So they have higher acidity than the beta, a gamma, and the alpha, right? I mean, the beta, gamma, and delta. And from here on out, we're going to be using the alpha, beta, and then later in later chapters, we're also going to be using the gamma and delta. So, and when you get to biochemistry, they use these terms heavily. So if you ever see anything in biochemistry where they're saying gamma acids or gamma amino acids or beta amino acids, that's actually coming from this nomenclature, the alpha, beta, gamma. Okay. The two main structures we'll be looking at is going to be the enols and the enolates. So if you remember the enols, that anytime we have a ketone, that ketone, and I probably should show it this way with a little arrow, right, has the possibility to tautomerizing tautomerization going back and forth between the ketone, right, the carbonyl and the enol. Okay, and we saw this in the reactions with our triple bonds, right? So if we added an alcohol to a triple bond, it formed the enol, and then the enol transformed into the aldehyde or the ketone. Now, in some cases, right, we see right differences, right? So if we look at this species, of course, the phenol here is going to be much more stable because it's aromatic. And if we look at aldehydes, aldehydes have more of the enol form than a ketone would. Okay. You know, and we can say that this one is near 100%, where this one might be, you know, I don't want to put the number, it's in your book. I don't want to put the number up. Okay. So aldehydes are more often form the enols just generically. If I want to form the enol in a reaction, what I need to do is I need to promote it. I need it to happen faster. And notice that they're always going to be reversible. So what you're trying to do here is actually kind of trap it. So if I look at my acid catalyzed, so if we think about the acid catalyzed process, and let me redraw this. We'll get the oxygen coming, picking off that proton, right? Then we end up with this species. And then if we think about that, those are both in resonance with each other. But then this proton can be pulled off here to get us to the enol. So by adding a catalyst, what we do is we get this reaction to occur faster, right? It's still going to be reversible, but we can get it to go faster. So think about this as an equilibrium process. And in the enol, the way to think about the enols is something like this, where we have A going to B, right? So ketone going to enol, right? If we can make this fast, right, what's going to happen? A is going to turn into B, but B is going to turn into A, right? And that'll go back and forth fast, right? But then what happens if B turns into C? What happens? A still turns into B, B turns into C, A turns into B, B turns into C. Does the reaction actually go forward even though I have a fast equilibrium process at the beginning? Yes. So when we think about enols, this is what's happening, right? We're adding the acid, or we'll see in a second, adding the base, right, to promote the transition from ketone or carbonyl to the enol form. And then the enol is what reacts to give us our final product, right? And I can, even though that first process is equilibrium, as soon as it reacts to form the enol, then the enol goes on to react further. Okay. We look at the base promoted. We get the oxygen attack. So base pulls the proton, right? We go through this intermediate species, we pick up a proton, and we go to the enol. Questions about those? So enols, kind of to sum up, enols could form a ketone or an aldehyde, could form an enol just by sitting there. I can make it go faster with acid or base, but it's an equilibrium process. When we go to enolates, the idea with enolates is now we've got a stronger base and then we form this species, right? So we do a deprotonation to form our enolate. Now, of these two, which one would you show more often? They're resonance structures, right? They're equivalent. But which one would make you more comfortable to show? The one with the carbon negative or the one with the oxygen negative? The oxygen. Why? Oxygen is more electronegative, right? So our standard form of the enolate is to show it this way. And again, if we use nomenclature from ions, right? Enolate, the ATE, it's an enol with an anion, right? So enolate. Now there's two ways that an enolate can react. Right? We could have oxygen attack. And we saw an example of that just above when we made the base promoted. But here, if we have the electrophile, right, we could have the reaction at the oxygen. So that's oxygen attack. We could also have attack at the carbon. And again, I'm showing the preferred drawing and enolate, right? They're both of those are fine. Right, to add the electrophile at the carbon. So this is carbon attack. Most of the reactions we're going to see are actually carbon attacks. One of the reasons for that is that the energy of the electrophile that they're going to attack is a better match for the carbon. And you'll see that most of the reactions we do are actually carbon-carbon bond forming reactions. So if we think about the molecular orbitals, what will a carbon's molecular orbital be more similar to? An oxygen or a carbon? Well, a carbon, right? So a carbon will have a similar energy diagram, energy levels as a carbon. So we see those reactions. Oxygen attack does occur. You see oxygen attack when you have proton sources, right? So if you did a proton, but if we think about a proton source with an enolate, what happens if I add a proton to an enolate at the oxygen? I end up with what? I end up with an enol. Right? And we'll see as we go through this chapter that enols and enolates do similar reactions. So there are times when you could protonate the enolate to form the enol, but the resulting reaction will actually be just the same. The enol will just behave just like it is an enolate. Okay. As we talked about above, right? And I'm going to use an aldehyde here so we just have one side. These two hydrogens, these alpha hydrogens, are very acidic. And one of the things we'll have to do when we're doing enolate formation is look for our alpha hydrogens, right? Identify our alpha hydrogens. And the reason that these are more acidic is that I can form the enolate or the resonance contributor. So instead of being an isolated carbon negative, right, it's delocalized to the oxygen. So we need to understand the pKa's of these. So we're going to do a little bit of referencing, right? So if we look at the pKa of an acid, and let's underline that, our pKa here, right, is about 5. If we look at an amide, an aldehyde, well, wait, let's go in order. Right, our water and our alcohols are both in that 16 range. So water is 15.7. Alcohols can be a little below water to usually a little above water, so 16. If we look at aldehydes, okay, and it always throws people off, right? But the most acidic hydrogen in an aldehyde is not the hydrogen attached to the carbonyl, right? That hydrogen in its sp2 carbonized. That's going to be very, very high pKa. But this alpha position is going to have a pKa of about 17. Okay, so a little less acidic than an alcohol. If we look at a ketone, right now we're moving up a little bit more in pKa, so about 20. Our esters, a little less acidic, about 25. Nitriles, around the same, about 25. They're usually slightly higher than esters, but in the same range. Amides, now notice on our amide that I'm not using any hydrogens on my nitrogen. So if I look at our functional groups, right, we've got the esters, our carboxylic acids, right? The most acidic is going to be the proton, right? So if I put an acid in there, I don't even have to worry about the alpha acids at first, right? So if I had a carboxylic acid and I wanted to react in an alpha carbon species, what would I do with the acid? I convert it into an amide, into an ester, right? Then if we look at our alcohol, so this gives us water, right? So that gives us about 16. Aldehydes and ketones are in that 17 to 20 range. And then our esters, nitriles, and our amides are in the 25 to 30 range. So if I took, this aldehyde and I reacted it with sodium ethoxide to form this enolate, would this be, right? So the question is this going to be reversible? Or is it going to be quantitative? Do you understand the phrase quantitative? Okay. Chemists don't like to say 100% because very few things are 100%. So we use the term quantitative. So quantitative would mean that this reaction would proceed to the products to a quantitative amount, meaning almost 100%. So the question here is, with this species, right, Is this going to be a reversible process or quantitative? And what decides that? What's going to decide that is my base. And what I need to know for the base is, okay, I've got sodium ethoxide. That's this. Oops. Sorry. That's this. But what's going to be the product once I pick up a proton? It's going to be this. So what's the pKa of that? It's going to be about 16. What's the pKa of these two protons? About 17. Is that a substantial enough difference to give me full change to the enolate? Or is that such a small difference that I'm going to have, and I'll put it in a different color, right? Equilibrium. Okay. And that's going to be one of the things I need to think about when I form enolates. Okay. So the book has a chart of the pKa's for the carboxylic acid derivatives with alpha carbons, right? The alpha carbon chemistry. This is a short list right here. You need to get familiar with this, right? And one of the reasons you need to get familiar with this is that we're going to be looking at these differences. So if this one's reversible, that means that this reaction could go back and forth. So is that a problem if I can form the enolate and have the enolate react and then form another enolate and have the enolate react? No, I can have a pre-equilibrium process. That's like what we talked about with the enol. But we also want to be able to do a quantitative process. What do we need to do a quantitative process? What has to happen with my base? The base, the conjugate acid pKa needs to be what? I have to see a bigger differential, right? So therefore, when we look at these, what we want to look at is huge differences. So in something like this, if I came in and I used a stronger base, and one of the favored one is this nitrogen. Why? Well, what is the pKa of a nitrogen? Well, the pKa of a nitrogen, right, is going to be around 35. So if we look at right, the pK here is going to be around 35. So now we have the pKa of these two hydrogens around 17, the conjugate acid pKa of 35, right? And pKa, what does the P stand for? Log. So what does log mean? That means 1,000, right? So when we had one difference, what was that the difference of? 1 order of magnitude, right? Well, what's the difference here? Whenever I see 17, that's 18. Is that just 18? That's 18 orders of magnitude. So that's 18 what? 1830 sets, right? So even if we look at esters or amides, even if I use something like LDA, I'm going to have, right, 5 to 6 orders of magnitude difference, right? So I've got a big difference. So when I use LDA or amides, I'm going to get a quantitative yield. Okay, and this is going to be important in some of the different reactions we see. So this acid-base chemistry is important to what we're going to continue to look at, okay? The first section of this chapter really kind of takes you back a little ways to some of the organic concepts. So I would encourage you to read it, I haven't encouraged you heavily to read a lot of things, but you should read this and read all the way through pKa's of the enolate chemistry, right? And that's where we stop today, and that's good enough for today, okay? When we come back, we'll look at the reactions and look at some of the difference of these, but it is important for you to understand these pKa's, put them on your flashcards, and to think about this difference between equilibrium and quantitative enolate formation. Okay.